Welcome everyone. I'm just gonna give it a minute or so just to let people in. Thank you all for joining us on a Monday morning. Oh, not Monday morning. Where am I?
Tuesday morning.
Tuesday morning. There we go. Oh, a bit too early. Okay, dokes. Yeah, I think we're good to start. So, thanks everyone for joining this session, which is our first session of the ZPNC stream at the GSE. This year we've got 18 sessions in total, so be sure to check them all out, and your support is very much appreciated. For the first session, we've got Ralph from SMT Data, who will be taking us through threshold reporting. As always, please do leave your session feedback. This session is 6AA, and I will leave a link where you can do so. And we would really appreciate any donations to our chosen charity of the year, which is NHS. And I'll also leave a link for that in the chat box as well. In terms of any questions, you can feel free to put them directly in the chat box, and Ralph will go through them at the end. Or alternatively, if you prefer to speak instead, just let me know and we can get you on stage and you can ask the question in person. And without further ado, over to you, Ralph.
Thanks, Piero. Welcome, guys. Good morning. And I'm sure there are no people in the different time zone. Anyway, it's a good afternoon also. I'm sitting in a nice corner. It's a cloudy weather. I see all the trees, not much of leaves still left out. So it's a nice cloudy morning. I'm pretty sure that every one of you will be having your cup of coffee. And then let's see that how we go through this presentation. As Piera said, my name is Ralph. I work for SMT Data based out of Denmark. And prior to joining SMT Data, I used to work in IBM, India, as a performance analyst. So I would like to share with you a collection of KPIs or whatever I call it as. Sometimes we call it as KPIs, sometimes we call it as performance metrics, sometimes we call it as focus areas or focus things. So it's basically a collection of certain attributes that influences the performance of either the system holistically or either the components of a system individually. So why do we need this threshold reporting? That's a question maybe you should ask. We have SMF. We have tons of data coming out of the SMF records. And we have vendor products. And imagine you have vendor products having the same type of information in a different format, in a different content, in a different layout. And we have the raw SMF data, and which has been translated into the performance databases. And you see that you are sitting on a stockpile of tons and tons of data. And imagine a performance analyst, you are supposed to take care of your LPARs, take care of the workloads, take care of the different subsystems. Would you be going through the whole stuff? So that is where, over a period of the last few years, based on the scholarly articles which has been published by people who have gone in front of us, I've got the names in the last slide. So this is basically a collection of recommendations of what we need to look for, how to look for the needle in a haystack. And that is what exactly it is. So this presentation is all about a potpourri of key performance indicators, a collection from various sources, which will probably help you to effectively and efficiently manage the performance function. I mean, this comes from my experience, and it is not necessarily that my experience should be the same as yours. I have a disclaimer at the bottom of the slide. While most of the thresholds are more generic in nature, but you see the dynamics of your environment may not be the same as the dynamics of everyone else. So the thresholds are generic, but the applicability of the thresholds may not be the same for all the clients and for all the environments. You have to take it with a pinch of salt. So that is why, but it gives you a good baseline. It gives you a starting point. So these thresholds, what you're going to look at, gives you a starting point. It gives you a pointer where probably you can look for. So that is where I start with the presentation. And we are going to look at a few areas, not everything. This is the agenda for the whole presentation. We are going to look at the parallel sysplex. We will look at the processor. We will look at the processor storage. And lastly, the file system, or we call it as a DASD. And when I was preparing this, I was trying to look at, and I had a few slides on the logger. So I just put it in. If we have the time, we will run through the slides on the logger. Otherwise, for the sake of an end-to-end review, for the sake of completeness, I've put all this together. So let's see how far we can go with this. Moving on to the parallel sysplex. Most of us know it's the heart of this parallel. It's a coupling facility is the heart of the parallel sysplex. It runs in an LPAR, yes, in a shared or a dedicated model. And now the hype is most of the LPAR most of the coupling facility configurations are being shared across, and that is because of certain other attributes, other technology enhancements that came in that offers a shared coupling facility environment. We will look at that in a few more slides. The coupling facility has got memory and has got pre-formatted structures, yes. And the OS that runs on the coupling facility LPAR is called the coupling facility control code. I will be only referring to this as CFCC, because by the time I start spelling out, pronouncing coupling facility control code, it's a tongue twister basically. So I will refer to the CFCC, and the coupling facility provides high-speed caching, list processing, and locking functions. I'm sure most of us will know about this, but what I'm trying to do here is setting the context to what exactly are the performance knobs, what exactly that we can tweak around. So I'm setting the context in terms of describing the coupling facility, describing the whole setup, so that when we come to the few slides where we talk about the KPIs, when we talk about the metrics, at least we have a little bit overview of what we're talking about. This slide is the component diagram, I call it as. You have the CF in the middle, and you have two systems, one on the left, one on the right, and you have the cross-system extended services, and you have the cross-system coupling facility connected to signaling paths, and you have at the bottom shared DASDs. So you can have access to the files from both the systems. And since both the systems are coupled together, we should have a common timestamp, which is provided by the common time reference. On the top, you see a couple data set, which has got some definitions in there. So this, at a very high level view, comprises the components or the bill of materials for a parallel sysplex. Now, this slide, we're looking at the configurations. The first one on the top left, if you look at it, standalone coupling facilities connected to sys1 and sys2. A variant, well, I think variant is a wrong word to use in a pandemic area, but still, okay, a variation or a different flavor of this configuration of what you see is you can have the integrated coupling facility standing out, not necessarily within this box. It can stand out as in a different place or in a different system or a different LPAR, and then it gets connected to the sys1 and sys2. Another variation of this is you have a standalone and you have an integrated coupling facility that's housed in the same box along with the sys1. One more variation is here, where we have integrated coupling facility that's housed in the same box as sys1, housed in the same box as sys2. You have different flavors. This is just like normal life. Yeah, you choose to have vanilla, you choose to have chocolate, you choose to have hazelnut, go ahead. But what type of configuration is acceptable to you? What type of configuration is good to you is definitely something you have to judiciously decide based on, I always say, three aspects: reliability, availability, and scalability. Choose your one configuration. And this session is not about deciding on what's the best configuration. This session is about we're just sprinkling the configurations on the sheet. And then we are going to go back and then see what is good and what is bad in terms of KPIs, basically. Now, in order to understand the metrics, in order to understand how the coupling facility works, it's a very simple flow of requests, how coupling facility processes that. Okay, basically an address space wants to have an access to the coupling facility, or services wants to make use of a coupling facility. It calls the related XES macro. It branches off to a specific module, builds a CF request, which verifies the caller, whether it's authenticated, whether it's a genuine caller, obtains real storage. Then it branches off to the appropriate XES module, passes the request to the CF work element. Subsequently, what happens is the XES module executes the CF request work element, determines which CF it should target to, obtains the subchannel of the CF, determines if the request should be asynchronous or synchronous. Again, this is based on the heuristics. The algorithms that has been designed by IBM based on certain capping models, based on certain overheads, based on the cost models which they have seen in the past. So every time you make a request, the service times are being captured and being used to build a model, so that when a new request comes in, the heuristics, it's learned by what has happened in the past. It either goes with the synchronous or it goes with the asynchronous, and then decides. And accordingly, it sends the command to the channel's subsystem. The operation is executed in the CF. The response is sent back to ZOS. The results are copied to the caller. This is a very high level overview of a request flow within a coupling facility. And you should ask why we are doing this. We are doing this because we want to understand where the bottlenecks are going to be and where we can tweak. Okay. Before we actually go to the slides on the coupling facility performance metrics, we want to introduce the links. Basically, a link is that makes the connection to the other side. And if you have a bottleneck there, you have a bottleneck everywhere, and you have queuing. So we just wanted to set the context on the links and the connections here. We started off with the intersystem coupling. It supports up to 10 kilometers without repeaters. It's gone. We came and moved into integrated cluster bus. This is the alternative to the ISC. And this again is no longer supported. Now we are in a generation where we have parallel sysplex Infiniband. So this Infiniband is the industry standard protocol to send CF messages across bidirectional fiber optic lines. And the single data rate supports up to 250 megabits per second. The double data rate supports up to 500 megabits per second. And this can span across 100 kilometers or 200 kilometers when you're using repeaters. The repeaters are, we call it as a DWDM repeaters. It's called dense wave division multiplexers or repeaters. So we see why I've put in the first intersystem coupling and where we are is we need to understand the progression in technology. Unless you understand the progression in technology, our performance metrics also evolves over the technologies that we're using, evolves over a period of time. What is applicable today may not be applicable tomorrow. And what I was seeing in the last 7 years, it is not applicable anymore. We will come to that later. I can show some examples of that. So Infiniband supports up to 7 subchannels, and new technology today in the newer machines like Z15 or Z14, you can add in up to 32 subchannels. The additional channels will help to improve performance without adding any physical links. So this is a slide on the link technologies. Now, again, we are in Z15. And while we are saying that we are in Z15, there is already a review of the Z16 model that's going on. Okay, it's some part of the world, there's a review of the Z16 that's going to come out sooner or later. Okay, anyway, that's not our topic for discussion. Now, in the new current technology, every time we come out the new hardware version, we always come out with a CFCC also. The current Z15 is tagged with the CF level 24. Okay, that's the newest or the latest technology. And what has it got? It has got enhancements on the FAIR latch manager. It's got SysID resiliency enhancements, and there was the dynamic dispatch option that came in, that was introduced in the EC12 and BC12, has been changed or it's made default. And there were some occasions where the CF was monopolized by some abusive workloads. And the new version of the CFCC helps to avoid the monopolization and does some monitoring, and so that it sends a message to the ZOS to queue and throttle new incoming CF requests so that we don't have a queuing time in the CF. So these are the major enhancements that came out in the Z15. I'm sorry, it's on the right-hand side of the slide. I don't want to play around with it now. And we're looking at the dynamic dispatch option. As I said earlier, we had three options. When we had three options, and dynamic dispatch thin came out in the CFCC 19. Okay, otherwise it wasn't supported earlier, and this was supported after the CFCC level 19. But what are the advantages of it? Of course, we had the three options. Let's look at the three options. The dynamic dispatch off, it means very clearly that the LPAR is completely under control of time slicing. So if there is no work, it just keeps on going and going and going. So basically, you're wasting some CPU cycles. Dynamic dispatch on is where it's a timer driven, basically. So when there is work, it wakes up at certain intervals, does the work, and then voluntarily releases the processor so that the CPU cycles are not being busy anymore. The last option was dynamic dispatch thin, basically based on certain events. It triggered then interrupts. The processor woke up, it did the job, and voluntarily gave the processor. So you see the three ways of doing it. And in Z15, the default today is dynamic dispatch equals thin. And this is the best option to choose if you are using a shared CF configuration. And that is what we see today. In a few installations where we have migrated to Z15, we always see that it's shared. We always see that the CF utilization 80-90%. And how they achieved it is because of specifying dynamic dispatch equals thin. But the question still remains, do we need to share your production? Do you need to share your QA? Do you need to share your test systems all in the same CF LPAR? Of course, that's your decision, but we see installations, and IBM recommends a dedicated CF environment for the production. Of course, recommendations are there, and it's up to you to decide what you want. But this is what is prevalent today. Moving on. Again, I'm not going to go through the slide. This is a slide on the current context. In the Z15 context, if you look at it, the Infinibands from the 12 lanes are moving out to one lane, bidirectional replacing them, and they are being replaced with integrated coupling adapter short reach. CE stands for coupling express long reach. And you see that EC12, BC12 machines are Infiniband only. And the ICA SR was introduced in Z13 late in the cycle. And your Z13 and look at the Z14, they don't support Infiniband anymore. They are only using ICA SR short reach and the coupling express long reach only. And you cannot go back. There is no N-3 connectivity from Z15 back to EC12 or the PC12 machines. That's it. Let's not go into the hardware and all those details. And this is one of the one of the notes. As of 30 June 2019, no hardware miscellaneous equipment specification is possible to Z13 to add any PCI coupling. Cannot be ordered anymore. Now, we have set the context of what the coupling facility is, set the context of what it does. Now let's look at what are the factors that affect the response time. The model of the central processing complex, that's what we call it as, or the CAC, where the ZOS image resides, affects the ZOS speed. Okay, it affects the XES, the cross-system extended services. Similarly, the model where the CF image resides affects the CF physical unit speed, affecting the operating system, CFCC. Type of CF links and technologies that you use, and the distance among the ZOS and CF also matters. Total demand at the ICF and CF links. Yes, this also has got an influence on your response time. Synchronous or asynchronous requests. Yes, you can see that synchronous is short and fast, and asynchronous is quite long. And the amount of data that's being moved per request, this has got a bearing. What are the structures that are used, lock, list, or cache? Again, is it activity in your zeros LPARs? Is it of low activity so that it wakes up as and when it wants and then does it? But the structures are duplexed, because this is basically for availability, or it's only simplex structures. Whether the CFs are shared or dedicated, links are shared or dedicated, the dynamic dispatcher, all this affect the response time of your CF request. What causes your wait time? Channels busy. UCWs, the unit control words we call it as. If it's busy, it causes a wait time. If the CF link path is busy, both the buffer is busy on the other LPAR, this also causes a wait time. Of course, there are 7 subchannels and 7 buffers per each link. Now moving on, the KPIs I call it as CFs shared or dedicated. Best for production is dedicated. Of course, shared used for test and non-data sharing production. CF level 19 and above, please use that, and choose the dynamic dispatch option as thin if you're using a shared environment. Now let's come to the utilization. Normal queuing models for a single server system. The knee of the curve starts at 30%. That's where, when you have a dedicated single engine, aim for 30%. Anything more than that, you may have some degradation. You may have some queuing. If you have 2 engines, aim for 50%. With dynamic dispatch equals thin, I have seen 90%. That they say it's quite normal. Okay, now coming down, a synchronous request within the CF. The happy values are 5 to 20 microseconds. Asynchronous requests, the happy values are 50 to 300 microseconds. And again, as I said, numbers may vary in your environment, depending on the configuration, depending on the technology, depending on the dynamics of what's happening. So these are just numbers which provide you with baseline, which provide you with pointers so that you can flag, you can understand what's happening in your side of the world, in your side of the systems. The delayed requests, we always look for, make sure that we have less than 10% of the total requests delayed. Anything more than that, investigate. Synchronous versus asynchronous, we have seen that. You can have reports and then find out how much of the requests are synchronous, how much of the requests are asynchronous, because each and every type of request has got its own pros and cons. When it's synchronous, the CPU spins idly until it gets the response back. Asynchronous, it just puts the request and forgets it. So it again depends on what is the type of request, who's the requester, and what it made. If he has made it, I want a synchronous immediate, there is no way it's going to be converted into an asynchronous. So again, but at least you should know what are the type of requests that's coming in, what are the percentage of requests that are coming in, how much time you are spending on the idle CPU spin when you're doing a synchronous request. Now, do I need a 1 CP engine or a 2 CP engine? Now, we recommend having a 2 CP engine, because if there are some long-running abusive CF commands, it holds on to 1 CP so that the other CP, if you have 2 CPs, the other CP at least can be used by other commands or other requesters for CF service rather than queuing here. Now, host effect, we call it as. A lot of installations have migrated to the Z15, and unfortunately, they forgot to move the CF environment to a matching technology. I've seen in installations today where we have Z15 and they're running on an N-1 or running on an N-2 or N-3. The recommendation is both the host and the CF needs to be dovetailed together. If it's not dovetailed together, you're going to have performance degradation. It's always recommended that when you upgrade the host, go at least be at an N-1 in the CF side. Path busy, make sure that you are at less than 20%. Link utilization, again, make sure that you are at less than 30% to avoid increase in the queue time. Sub-channel delay, aim for anything less than 10%. If it's more, add more sub-channels. These are the KPIs. And we're not going to look at anything down here. As the distance increases, you have to add 10 microseconds per kilometer. So that is what you see here. Now, looking at the structures, performance of the structures, we have the list, your lock, and the cache. Looking at contentions, true lock contentions aim for anything less than 2% when it comes to the database side, anything of 1% when it comes to the CIC or the GRS. True lock contention happens for actual resources, like I want to update a DB to row, a page, and someone is also holding on to the page. That's true lock contention. What you can do about is look at the application programs, look at why this guy is holding on to that specific page for a long time. Make sure that he comes in, updates it, and goes off. Does not take an exclusive lock for a long time, does not hold the resources for a long time. That's the only way you can do it. Whereas in false contention is nothing but your hashing algorithm puts in a slot where it's already used by someone else. So here you have to increase the table structure. You have to increase the directory structures. So true contention is here, false contention is here. This should be aimed for anything between 0.5 to 1%. Transport classes, this is the last slide in the coupling facility. Retry should be 0. Buffers unavailable field should be 0. Average queue length should be anything less than 1. Average transfer time should be around 0.6 milliseconds. And we were tinkering around with the buffers, 2 small buffers, and then we had big messages coming in, it has to expand. And we had small messages and big buffers, we're losing space. Now, in ZOS version 2, release 4, you need not define, monitor, and tune to manage the transport class definitions. It's already being done by the specific pseudo transport class, which takes care of it. And there is a new XCF function, XTC size. XCF will intermix signal sizes and manage the signal paths accordingly. With this slide, we close the discussion on coupling facility and we move on to the processor. This slide introduces you to the terminology and LPAR busy. Basically, it's a dispatch time of the physical CPUs that are assigned to the logicals. And if you're looking at it, yes, it is basically based on the logical CPU online time. So this is clear cut. The LPAR busy time, when you look at it, it's quite clear, it's easy to understand. But coming to the next bullet, the MVS busy time. This is where it's a little bit more confusing. Okay, when you look at the LPAR busy time, the instrumentation, the measurements is from the instrumentation from the hypervisor. When it comes to the MVS busy is CPU busy from the perspective of the operating system. So essentially, it is the amount of time that ZOS did not go into a wait state. Okay, in a perfect world, in a very ideal environment, in an ideal world, which we never see, of course, we always expect that both LPAR busy and the MVS busy will be the same. Unfortunately, not. What happens is, there are times when ZOS dispatched work to be run on a CP, and the Prism decided to take away the CP out. So what happens is, the ZOS clocks keeps ticking, and the LPAR clock is stopped, basically. So that is where when we see the difference. And if there is a significant difference between the MVS busy and the LPAR busy, that is a sign or an indicator of latent demand. We use it as an indicator for latent demand. So that is exactly terminology is what we are trying to define, and we are touched upon on the latent demand. And let's see what it is. As I said, if there is a significant difference in MVS busy and the LPAR busy, it's because of latent demand, and it's because of, and it can be influenced by weights and logical CPUs assigned. And in today's technology, you need not worry about it if you have vertical highs. this is more applicable. The latent demand is more applicable for vertical mediums. Now let's come to the last one. We're looking at a warning track interrupt. This happens when the Prism decides to take off the CPU. It decides to take off the physical CPU. It says that, okay, I need the CPU back. And within this grace time, return it back. So it gives a warning basically. So this is a warning track interrupt and very specifically applicable for only the vertical mediums and for the vertical lows. Now, looking at the latent demand, what's the good healthy value? We have CPU equivalents. If it is anything greater than 2 to 3 times the number of CPUs, if you have 3 engines, if it is anything, the CPU equivalent is greater than 6 or anything ranges from 6 to 9 or anything greater than 9, I would say that it's time that you look at what's causing the queue. It's time that you start addressing the queue, addressing the bottlenecks. So these are the healthy values here. Now, saturation design point concept that was developed by IBM. And it is basically says if my hourly utilization is 80%, how often was 100% reached during the smaller interval? This is the formula that's given. Average hourly utilization divided by the peak minute utilization multiplied by 100. Well, now how does it help me? Okay, in terms of performance management, what I keep looking for is during the hourly average, my hourly average should not exceed the SDB threshold. That's from the performance point of view. Now, looking at the capacity point of view, when I'm resizing the processes, when I'm revisiting the size of the processes, I need to ensure that the sizing, or when I need to have sufficient processor capacity that avoids exceeding the SDP threshold. So these are the 2 things that comes out of the saturation design point. Now, the last 2 items are the capture ratio. What is the capture ratio? We count the pennies. Type 72. We count all the CPU seconds used by the various service class periods and try to account it under the effective dispatch time. It never tallies. It will never ever tally because there is always that there will be a difference. So basically, what is capture ratio? Total capture time divided by the total CPU busy time. And again, what is the happy value? When we started looking at it from probably 10, 15 years back, IBM recommended saying that, yes, if you're having a capture ratio of 80% and above, it's good. But today, we are looking at anything less than 90 warrants an investigation. And why? Why? Where do we get this uncaptured time? Uncaptured time could be because of slip traps, could be because of SRM invocation interval. There's a parameter called RMT Tom, which you can look at what is the default, because basically no one touches the defaults. We inherit the defaults. We are scared, we are feared, and we don't want to touch any of the defaults. So, but now, if you're having a high uncaptured time, it's time you take a look at the default parameter settings, slip traps, paging, contention. All this causes more uncaptured time. Okay, so that is something where you have to look at. My happy values are anything less than 90%, just leave it. I mean, anything less than 90, yes, you have to look at it. Anything greater than 90, just leave it as it was. Now, I'm an old-fashioned guy. I don't have a ponytail. I don't have a long hair because I don't have hair. So now, when I always used to do a health check, I always look for short CPs, short CP engines. This was prevalent in the Z9 and the 990s. Unfortunately, does not exist anymore. The reason is now we have tightly coupled systems. We have affinities with the processors. When we have vertical highs, now it is attached or it is got an affinity to a specific logical processor. The physical and the logicals are tied together. So the short CPs does not exist anymore in a vertical high environment. It may not show its ugly face in a vertical medium or a vertical low also. And what we need to keep looking at is this is no longer relevant in this case. Okay, short CP ratio is no longer applicable, and it is not necessarily that when an engine is supposed to be taken over, we have the mechanism called the warning track interruption, which we saw earlier. So there will be a message saying that I'm going to take off your CPU. So it gives enough time for the task to clean up, do the housekeeping, and then hand it over. The other bullet is ratio of logical to physical. I always look for a 3:1 ratio, a good, healthy ratio. It does not mean that you cannot go any more higher. You can go higher, but as a capacity planner, you have to make sure that you have higher ratios, you're going to have higher virtualization costs. That's going to reflect as your LPAR management time. Just keep that in mind. Hyper dispatch. We have seen the set weights to optimize vertical heights to improve performance. It's very realistic. Last year, I was doing a technical health check for one of the clients, and he had his weight set that was very close to around a 1.4 guaranteed process. And he was sitting in a box which had a QA system and had two other test systems. I, in fact, pleaded with him to shuffle the weights in single digit, just add 7 more to the production and take off the 7 more from the test system. And imagine what we had was, we had 1 vertical high for the production. This is one of the finest controls, which for some reason, I'm going to pose a question to you. Okay, I'll come to the question later. So set the weights accordingly so that you can optimize the vertical heights. Revisit the weights for high CPU LPARs. Now imagine your batch is having a peak usage. Why don't you have automation in place? Why don't you play with the weights after your 9 o'clock, 9 p.m. so that increase the weights and have increased vertical highs, process your batch, and then when it comes in the morning, go back to your old weight. So revisit the weights for having high CPU LPARs for effectively and optimize and using your CPUs in an optimum way. Optimize LPAR entitlement for vertical assignment. Check for unused LPARs. Need to deactivate unused LPARs to reallocate the weight to vertical heights. Now, the question for you is, I always think about this. When we are doing the LPAR definitions in the HMC, why not a message pop up saying that, hey, can you shuffle the weights so that you're going to get a virtual high or vertical high, and you're going to get a vertical medium instead of vertical medium? If that type of a facility that's added when I do the LPAR definitions, I think we can definitely, it'll be a quick and easy way to optimize the vertical highs and vertical mediums, or the assignment or the affinities. It's a question for IBM probably. How is it? Why is it not possible to do it when we do the HMC definitions? The warning track interruption facility. I love SMF, and these are the fields which you'll have to look for. Sorry. This shows very clearly how many times Prism asks ZOS to return back and to return back the physical CPs. This is a time when it was not able to return back. This is the time how much milliseconds it was under the control of the warning track interruption. So this is very nice fields. If you want to track this, you can do this. That closes our discussion on the processor, and we are moving on to the next area of processor storage. A lot of things has happened in the processor storage. We were running machines with probably 4 GB, 8 GB. Now we are running at 128 GB, and now we are at 4 terabytes. Imagine a Z15 with 4 terabytes of memory. So my past thinking is gone. My past assumptions are broken. My foundations are already demolished, basically. I used to live on unreferenced interval count, which is no longer valid. Let's go on. Okay, this is a layout of the processor. I mean, it's a layout of the process storage. What we're interested is below the line, above the line, above the bar. This is 2 GB line. This is a 24-bit below the line, and this is the 31-bit above the line. So this is a layout of the processor storage. We're not going to go through in details of who's sitting where and what is it. We're just setting the context for the subsequent discussion of the process storage. Now, as I said earlier, unreferenced interval count, it basically a measure of how many seconds this specific frame was not being referenced. Okay, so in the earlier days, it was a good measure, it was a good indicator. Higher the value, less contention. Lower the value, it was more contention. Unfortunately, when we have 128 GB to almost 1 terabyte in the system, this is no longer valid. Okay, you can just do away with this and then look for, now today, what we have today is the frames are being classified as high, medium, and low frames. Look for the average. Look for the minimum. What is the average and minimum of the high frames? What is the minimum average of the medium frames? What is the minimum average of the low frames? And I saw in some documentation saying that what is classified as low is something that has not been unreferenced for more than 150 seconds. And what is medium is something that has not been unreferenced for 20 seconds. And anything beyond that comes into the high frames, which is protected, or it's not critical, or it's critical and it's not protected. So that is old documentation. I'm not sure whether it still is the foundations for classifying of high, medium, and low frames. But what is good for you is to look at the average and the minimum of the high, medium, and low, and have your own baselines. Now, this is another metric, available frame queue. Of course, this is basically you're building a cache, we're building a buffer, we're building a cushion. Now, this is a parameter which we normally look at, basically. The first parameter is, of course, it's called MCC AFCTH. It's called available frame count threshold. And the first is a low value, and next is a OK value. Of course, there's a slight difference in the formula here, but let's look at it. Okay, basically what happens is when the real frames goes, okay, let's take this example. When it hits around 50, then the real storage manager knows that, yes, it has to reclaim some pages. It needs more pages because we are at the low value. So it starts stealing pages until it reaches 100, until it reaches the OK value. So we look for, this is still old, the defaults are old. So we recommend that it's 4,000, 4,500. And again, AFQ metrics are the best indicator. Review the minimum, maximum, average available frames in the interval. And as I said earlier, this is not a straight formula, because how memory management does it is basically it uses the low value, low value, 400, 0.2%. So that is the variation, and it calculates accordingly and sets the low value. Similarly, for the OK value, it uses whatever you have given, 600, 0.4%. So whichever is best, it picks up the numbers. But as far as, let's forget the underlying formulas for that, but let's look at these metrics are the best for you to review at any point in time. Now, page stealing. Assigned page has to go out, basically. You're making provision for others. And there's a demand. So this is what happens. The real storage manager starts stealing frames from the unreferenced for a long time and then gives it to someone who needs it. And it uses the global least recently used algorithm. Okay, and again, this is just to set the context of what happens in stealing and why. And the problem is, who is being hurt? He doesn't have a space to come in. You have not invited him inside. To invite him inside, you need to provide him space. And there is no space. And he has been standing outside. So there's been a page fault, basically. He doesn't have a page, and then he needs something. So that is where it's coming in. So he's being hurt. Look for people who are being hurt because there has been more pages who have been fixed. Maybe pages are being fixed, and maybe pages are not being released. So this is a guy whom we have to help out. And swapping is no longer applicable in the current systems. The entire physical swapping is on the local page data sets, and swapping is done in real. That's very important. It's done in central storage. Look for the number and type of swaps. That's it. Now, as I said earlier, the old dimensions of memory management are no longer applicable because we were operating at 4K pages. We no longer go with 4K pages. We have the ability, we have the luxury to have 1 MB pages. We have the ability to define 2 GB pages. Imagine 256 4K pages within one boundary, within 1 megabyte boundary. IBM recommends you to go for large pages because of certain reasons. We look at it. So we can define large frame area, that is 1 MB pages. We can define this is pageable large areas, large page areas, we call it as. So after you define this, this is automatically defined based on the online storage that's applicable during IPL's time. 1/8 of the online storage is available as pageable large page areas. And this can overflow into a large frame area. This can, if it grows, it can overflow into this area. So now you have to have metrics to handle this. You need to have metrics to understand what's happening here. You need to have, now what happens? It is not only the large frame area we introduce big pages, and then with comes in another dimension of, it's not the same old memory you are looking at. We introduced storage class memory. That's a new memory tier. This came with EC12. The storage class memory came with EC12, and then the virtual flash memory came with probably Z15. I mean, probably the Z14. So this is where we are in terms of new technology. And if you have new technology, you need new metrics to handle it. And what are the new metrics? Basically, if I'm looking at from this one, LF area, I would look at what is the size of this, what is used, and what is available. Similarly, what is the size of this? Pageable large page area. What is the size? What is available? What is being used? These are the metrics I would look for. Now look for SCM and virtual flash memory. I would look for the slots that are used, slots that are available. So these are the new metrics you need to focus on in the current technology, in the current era of storage management. And again, track minimum, average, free memory, unused memory. Paging, page data sets. We have seen this, nothing much has changed. Fortunately or unfortunately, nothing much has changed. Parallel access volumes is key to performance. Recommended minimum of 4, but more is better, more and merrier. Managed as a circular queue. Unfortunately, this still holds good. Keep the slots used at 30% less, because the contiguous slot algorithm somewhere dislikes anything more than 30%. We do not know what affinity has got, but this slot algorithm has not changed. I don't remember anyone saying that it's been changed, but we are sticky to this less than 30%. Keep all locals at the same size to improve slot selection. This is on the page data sets. While I was putting together this specific set of slides, I was looking at something that came up when health check, as part of the health check. And I thought, let me also touch upon this. These are the common health checks which you can do when you're looking at your processor storage. And this is automatically, you can subscribe to this, and it works well, basically. And what it says is, if the CSA size has changed in the last IPL, it flags out an error. If the threshold, when the CSA is getting full, you get an alert. SQA limit warns if SQA size is too small. Similarly, when the private size is small, when the CSA is small, you get flags out error messages. Not error messages, flags out warnings, it flags out information messages. SQA threshold warns if SQA is getting to full. Okay, this is the largest free space that's available in the CSA. Basically, this is some sort of alerts, some sort of metrics, some sort of information which you can get on the basis of subscribing to health checks. That closes our discussion on the processor storage. We call it as a memory, because again, this is also processor storage, but this is the file system in the newer world of things. We used to call it as DASD, Direct Access Storage Device. I'm still old-fashioned, as I said. I still call it as DASD, and this is my file system. Okay, and this is where we are today. Okay, let's look at now again to set the context of DASD. What happened? DASD evolved in the past probably 50 years. 1974, we started on the Winchester drives. When I was aged enough, matured enough to start working in the mainframe environment, okay, in 1985, I was working on the 3380s. Then came the 3390s. Then came the 3390 Mod 2 and Mod 3 devices. And before we hit the turn of the century, we had RAM-ACK drives. Before we hit the turn of the century, as I said, 1999, we had the enterprise storage system, the SHAC. And what happened in all this stuff? The progression of having from 2 gigabyte drives to 5 gigabytes to 40, and the SHAC system was a 40 gigabyte, and which could scale up to 11 terabytes. Whitney Bowles was the first client to buy this. So imagine we have expanded on the capacity of the drives. And today we are in DS8K, that was the old version. 8800 came in, and today we are in 8900F, which promises 18 microseconds of response time. Imagine where we have come. We not only increase the capacity of the disk, the IO, the internal bus that connects this IOs has also drastically changed. When we started this, we evolved from a self-timer interrupt technology that was only giving you a speed of 2 gigabits per second. And today, we're running on a PCIe generation 3. PCIe stands for Peripheral Connect. Okay, Peripheral Component Interconnect Express. We are running on a generation 3. That's what is applicable in Z15 today, which gives you 16 gigabits per second. Just the previous version of Gen 2 gives you only 8 gigabits per second. Today, we have slots in Z15 for almost 12 PCIe Gen 3 cards, 16 gigabits per second. You see that? We have increased the capacity of the drives. We have the interconnects, the bus that takes those bits and bytes are also faster now. We have changed the technology, and that is what has changed our fundamentals again. Okay, let's quickly look at the DASD IO flow and then go through the rest of the stuff. The user address space translates application requests to access method services. Basically, it's either vSAM or QSAM or BSAM. Access method services builds the channel commands, translates the virtual address to real address. A start sub-channel command is issued when the IO is started. It wakes up the IO processor. Request is sent by the IO processor to the storage controller via the FICON directory. You should ask me why the hell you're using FICON. I'll come to that later. If data is available in the storage controller, it sends back the response. If not, request is passed to the disk. The disk completes the task and notifies the storage controller. Storage controller informs the IO processor, who in turn wakes up the CPU, which then invokes the address space. Now, this is a very simple flow of IO. Let's look at what has happened. These are the components of the response time that we are looking at. Based on the IO flow, there's IO is queuing, there's a pen time, there's a disconnect time, and connect time. To understand the metrics, you need to understand this. To understand the KPIs, you really need to go through this. Device is in use by ZOS. Device reserved from another system. A command response delay. A storage access processor overhead. A disconnect happens when there's a miss. A synchronous remote copy. Multiple unlegends or parallel access volumes. Conflicts. Control unit busy. Unfortunately, it's not there anymore. I'll come to that. Channel and data transfer protocol. Now, this is the IO. This is the fundamentals of our response time components. And now what happened? We buried SCON. Enterprise system connection is no more. After 2011, it has been replaced with FICON. This is fiber connection. This is enterprise connection is gone, and most of the things came out from the enterprise world, connection world, and now we are in FICON. So the response time components has changed. What you see here may not be the same here. IOS queuing is the same. Pen time, all channel path busy. FICON does not exist in the FICON environment. Director port busy. FICON does not present a director port busy. CU busy is non-existent in modern controls. Of course, it hides it somewhere else. Okay. Command response delay. Device busy delay. Disconnect time is the same. Connect time is the same. So this is what changed in our fundamentals. Now, these are the metrics. Response time. Response time is nothing but service time plus wait time. Well, what is service time? Connect time plus disconnect time. What is wait time? It's a queue time plus pen time. Of course, in a new environment, this could be 0. Now, what is a queue time? It's a disconnect plus pen plus OSQ. Imagine when we started our life, and even today, if you're going to look at 100 plus gigabytes of storage in a production environment for a specific application, we used to have 3,000 plus logical volumes. Is there a way you're going to do or going to find what is the ugly dastardly? No way. You cannot do that. So what is the best approach? I attribute this to Tom Barrett-Bass. I think he was the one who coined IO intensity and who brought in this queuing intensity. He was the one who said that the best way to look at 3,000 plus logical volumes and decide on the candidate list what needs to be focused on is just multiply the response time of a device and then with the activity rate. And this gives you a very good indication. So out of the 3,300 volumes, you can probably, at every 15-minute interval we are looking at, you multiply this, get the IO intensity, sort it out by descending IO intensity and focus on the top 10. And that is what we did. Unfortunately, today, there is not much of storage, just programmers who understand storage performance anymore. Queuing intensity. This also gives you a very good indication of combining the activity rate and the queue time. Basically, imagine I have a disk which has got a response time of 20 milliseconds. So what? If its rate is only less than 1 activity per minute, it doesn't really per second. It doesn't really even don't even need to look at it. But imagine you have a disk which has got a response time of 7 milliseconds and is pumping in transactions, pumping in at a rate of around 200 per second. Then that is the disk which you're going to look at. That is the focus area where we're going to look at. Techniques to reduce response time, software techniques, buffering, compression, striping. I'm not going to read through this because today we have hyperlink and we have Z-HyperF. This is high performance FICON. Hyperlink today is Z15's new technology. You just connect direct to the storage device. Just connect direct, that's all. There's nothing in between. So there is no latency involved at all in this, but you have a restriction of within a 150 meters. That's the restriction. Now, coming to the happy values, response time, I look for something that's less than 1 millisecond. Of course, depending on the online or batch. Imagine a batch, a DB2 batch, running a prefetch and fetching almost 200 pages. I cannot expect to have 1 millisecond. So that's why be judicious, be cautious when you're using the numbers. 1 millisecond, subjective. Don't hang me later saying that you told me that it's going to be less than 1 millisecond. Of course, I told you, yes. But again, depending on what is running, what is the environment, what is the technology you're using, and how good is your storage boxes and technology. IO is queuing. Look for something, anything greater than 0.1 millisecond needs investigation. Pen time, you should not see this. If you see this, needs investigation. Disconnect, anything less than 0.5 milliseconds. Connect 1 millisecond. This is a wonderful ratio that came out. The response time versus the service time should be close to 1.1. Anything more, anything less, you look for where we are spending our time, where you're wasting time, and then look for that and nail it down. Anything in queuing intensity, anything greater than 100, considered bad for the logical volume. Device busy, 70 to 80%. When we were operating, it was only 30%. They said, no, don't go anything more than 30%. Now, today's technology, we can go up to 80, 70 to 80%. Be happy. Channel utilization, always stick to 50 to 60%. We always say that, yeah, we have multiple things, but unfortunately, the queuing model doesn't work anyway. When you have a single server model, it works at 30% good. And anything more than that, of course, 60, 70% is where the theoretical models say that after 70%, you should be seeing queuing in the rest of the components, not only in your specific component of Dynasty. You should be looking at your rest of the components. Surrounding ecosystem also suffers because of queuing. So we can as well say that, yeah, you can run 100%, no issues. But your queuing model specifies very clearly that after the 70%, you start seeing wait times across. How good, how bad, how ugly it is, we will not know until it explodes. The goodness of Webometrics, it depends. Good to analyze at the PCO or LCO level. With this, I close the DASD discussion. As I said, I think I have under 5 minutes. If Pierre also says that it agrees it's 5 minutes, or I do not know what it is. Logging, system logger, I just put together the slides. These are the logging services. These are the components. And these are the components within the logging services, and which is basically used for SMF loggers, and some other things also use the logger components. The exploiters, we call it as the CICS, SMS, IMS, RRS, LogRec, OpenLog. SMF uses these exploiters, and we have wonderful performance data coming out of these records. 72.3 gives you on the IX logger. 74.4 gives you on the CF logger structures. The DASD activity comes from the 74.1. Cache comes from 74.5. and the logger activity comes from 88. And we have the next slide. And these are the conditions which you need to look on if your shop uses logger extensively. Look for the number of structureful conditions. Look for the number of times offload initiated because 90% list structure was full. Look for the number of times the staging data set height offload threshold was hit. Look for the number of times when the staging data set filled up, and the number of times the structure was rebuilt. Now, these are the key fields which I would normally look at. The bytes returned to the log stream, the bytes returned to the DASD, the number of times logger had to suspend before writing to log stream to DASD because of a previously initiated write to DASD. Now, this is the number of structure rebuilds completed for this log stream, the number of times the logger detected structure full conditions for this log stream. This is the number of times staging data set threshold hit for this log stream. And this ETF, number of times staging data set full condition hit for this log stream. Each and every one of this is a key performance indicator. EFS, number of times system logger initiated an offload due to the list structure in use entries reaching 90% full because your list structure is small. EDO, number of times offload was explicitly requested. And again, we move on to the last field. Number of times system logger detected a staging data set, async buffer pool, conditional log stream. These are the key fields which you can probably look at if you're running a logger, if you're running a shop has got logger issues, and then probably you can look at how you can tune it. And I had to run through the slides because I think we are falling short of time. We had another 2 minutes. And then just to go back to this one, the logging allows subsystems to record certain events. I'm just setting the context now after we discuss the crux of the whole thing. The component of ZOS that provides logging services used by ZOS system, used by transaction processing environments, used by applications. Services are saving of logging data, retrieval, automatic archival, ability to manage a single merged log from multiple instances of application, management of logging facility. I think with this, I close the presentation. Any questions? Okay, before I close, I have to thank the following people. Kathy, David Bedden, Elvira, and the amount of literature what Peter, Scott, and Todd has gone through. This was the light that shone for me in my last 10 years of performance and as a performance analyst. And Kathy, and if I look at David Bedden, they were too good because they answered my questions. Even when I sent her questions 2-3 weeks back about, hey, can you technically confirm, is this right? Although I was not an IBM, they just came back within the same day saying that, yes, this is right, or this is what today we are doing. There are certain aspects which has not been documented, in the last few years. So that is where I had to talk to them, and I talked to them, and these guys provide the inspiration. These guys provide the enrichment for us, the enlightenment for us on specific areas. When you have time, please go through their documents, please go through their reports, please go through proceedings. And last but not least, I have all the role models in my current organization who keep inspiring me. Thanks to everyone. Thanks for your patient hearing. Thank you.
Thanks very much, Ralph, for the presentation. That was very informative, especially the examples that you shared as well. We're quite limited on time, but I can open up for questions. Probably we'll have space for 1 or 2. So just a reminder to everyone that's tuned in, you can open the chat box and submit your questions. Or if you want to speak, you can come up on stage. I can unmute you. So just let me know in the chat box as well. You can also open up the chat box as well, Ralph. I think we've got a few comments from Martin Packer. Is talking about your definition of coupling facility utilization.
Okay. Yeah, Martin, careful definition of CF utilization was shared. Yeah.
Perhaps I can ask Martin to unmute and then maybe elaborate.
Good morning. Can you hear me?
Yes, Martin.
Sorry to give you a couple of actuallys, and hopefully they're useful ones. So the first thing is your 80% coupling facility utilization. That, I hope, would be based on the standard RMF definition of utilization. The problem with it, and by the way, I agree with it if that's the case. The problem with that definition is it doesn't do so well with shared coupling facility engines because it doesn't understand time when the coupling facility L part isn't dispatched. So depending which utilization metric you're using, the 80% is either good with the standard one or the more useful definition, which is to do with 77 type 1 view. I wouldn't go 80% or anything like, but I'm sure your intention was to use the standard RMF metric of utilization.
Yeah, thanks, Martin, for that. But can you, because I've seen installations of 90, I've seen it 80, and by IBM recommendations, when I was reading with David Rafton's paper, it was around floating around. So what is your best call on this specific metric?
Right. So if you are using, as I say, the standard RMF metric, the other 20% in your 80% is basically time when the coupling facility LPAR is spinning, looking for work. Right. But if it's not even got the engine, then obviously that time doesn't exist, which is why I tend to think about don't have the pool be more than whatever you want to say, 40, 50, 60% depending. And don't end up with a situation where your requests in the coupling facility LPAR in question, are getting elongated. That's the key thing. So
yes. I fully agree, but we have a very hard time convincing people about it, convincing technical guys, convincing 20-plus-year-old system programmers saying that, hey, do this. No. They say, no, this is new. We want to share it. We want to do this. So it's high time.
I know. Coupling facility design is a key point. I'm glad you spent time on it, actually.
Thanks.
Can I move on to the other one? The other one is something that Elpida Sartos, IBM fellow who worked on the design of this, shared with me a long time ago. It's the high, medium, low frames. Those aren't measured. Those are estimated, which makes them a bit difficult. And the reason why they're estimated is simply because we replaced examine every frame with an algorithm which looks much like the old expanded storage algorithm, which basically understands old and new frames. So those numbers are estimated. I entirely agree, by the way, with the metrics you're suggesting to use, which are, what's the minimum available, and perhaps relative to the average available. So I just wanted people to understand the high, medium, low frame categories, which I used to major on a long time ago, really aren't counted. They are estimated and therefore really not very reliable, but they're interesting and vaguely useful.
Thanks, Martin.
Sure. Let's see if I can mute myself now for a few minutes.
Thanks very much, Martin. So I don't think we've got any other questions or comments coming in. So with that in mind, I just want to ask everyone to please leave your session feedback for this presentation. Just as a reminder, it's session 6AA, and you can leave the feedback via the website or through the link that I've pasted in the chat box. And also, if you want to take part in this year's raffle, then all we ask is that you help us support our nominated charity of the year. And the link for that is in the chat box as well. We are going to be back in here in about 20 minutes to hear from Martin Packer. So he's going to be presenting on useful open source performance tools. So I hope everyone can make that session as well. And thanks very much, Ralph.
Thank you
for your time and the presentation. Take care, everyone.
Thank you.